about finding paths in a graph. Here, we can see that in NetworkX, it's actually relatively easy to figure out what the path is from some starting point to some ending point. I've modeled a graph connecting A to B, B to C, C to D and E, and E to F and G. And I've given them all uniform weights. And if you look at this, you can see that this is pretty linear, at least as it's written. Let's eliminate this for a moment. A connects straight through to G, through C, and there's only one little choice up there that then dovetails later. You can see that I can add a fast path from D straight to G, but I won't leave that in there yet. In NetworkX, I can ask for all simple paths. And all simple paths gives me every possible way I can get from some starting point to some ending point. Here, if we reintroduce this node, you can see I can get from A to G in two possible ways. I can also ask NetworkX for what the shortest path is. And the default mechanism that it's going to use is the number of hops. I can even ask NetworkX for the shortest path with a weighting, which means that if I make it more expensive to transit through D, then you can see that it'll choose to transit through the longer path through E and F instead. These are all fairly easy to use, and under the covers, what shortest path is going to do, it's going to figure out how you want to compute that shortest path, if it's from some starting point to some ending point, and it's going to figure out from the directedness of the graph which of the algorithms you're going to use. But I want to talk a little bit more about where graphs show up outside of NetworkX and where this idea of paths and connectivity may show up in your work. You may have seen a formulation for a graph that looked like this, a matrix. In fact, if you've ever done anything with, say, Markov chains, this is a Markov transition matrix. It gives you the probability of going from some state to another state. So from state A to back to itself is 50%, from A to B is 25%, and from A to C is 25%. And you can see I've modeled this. You can see, I guess this is symmetric because you can see this is a matrix that's symmetric across its diagonal. One of the things that you might know about this structure is, if I multiply this structure, if I matrix multiply it by itself, I get the two-step transition from some starting point to some ending point. So what this tells me is it is a 37.5% probability to go two steps, first from A, ending up in B, passing two steps, either going from A to A and then A to B, or from A directly to B. This is what these transition matrices allow us to do. And so what we can see from this is we can actually model a digraph, not just using our NetworkX, but also using NumPy or SciPy. The problem that might arise is if we have a digraph that looks like this, and you can see there is some connectivity, A to B to D, A to C to D, and in this matrix, we're putting a 1 anytime there's a direct connection, and a 0 anytime there is no direct connection. We can find what the one-step connectivity is by raising this to the first power, the two-step connectivity by raising it to the second power, the three-step connectivity for the third power, and so forth and so on. And we can even see, is something connected to something else? We just may not be able to see what the shortest path is or what that shortest path's number of steps are. This is a very valid way for us to identify fixed-step connectivity from some starting point to some stopping point. But one of the problems with this is it is very memory intensive, because if I have 1,000 nodes, then I need a matrix that is 1,000 by 1,000 in size. And one of the things you can see from this structure is it's mostly zeros. This is what we might call a sparse graph. It is a graph which doesn't have that many connections relative to the number of nodes that it has. And this matrix formulation of it is fairly efficient. It's contiguous in memory. Performing matrix multiplication may be very fast, but it is very wasteful if this thing is very sparse. And so what I might choose to use to model my graph is instead SciPy's sparse graph. Here we can see a sparse CS graph. And if you look in SciPy, you can see the same sorts of algorithms that you are used to finding in NetworkX.algorithm, like shortest path. Here, instead of modeling this as just a NumPy and D array, I create a graph from the dense representation, and I can ask this structure questions like, what is its shortest paths? What are the shortest paths giving me the predecessor nodes? What are the shortest paths giving me the indices of that path? I can do all the things that I expect to be able to do with a normal digraph, but modeled differently. But your question might be, oh, well, now I have this great contiguous modeling that doesn't have the downsides of NetworkX using SciPy sparse graph. What's not to love about this? Can I use this anytime I want to model a graph. Well, it turns out that the sparse graph is basically modeled using what we might call an adjacency list. There are two rough ways for us to implement a graph, and it's going to have direct consequences on the algorithms and the efficiency of those algorithms that we choose. The first is to have a written out structure like a matrix. Every connection to every other connection, a 0 or a 1, or maybe some edge data. The second is to just store what is connected to what is connected to what is connected to what. The latter is more memory efficient because you only store the connectivity. But it is less time efficient because the data is not contiguous. You can't just do a simple matrix multiplication in order to find two-step connectivity or three-step connectivity. You have to do a lot of pointer chasing. And as you may know from reading about things like graph databases, this graph structure, especially with the adjacency list implementation, is one of these pathological structures that's just really hard to make efficient. There's so many memory accesses you have to do because you have to say, okay, here's this connectivity. Okay, now let me find the next connectivity. Okay, do this memory access, do this memory access. And unless you're guaranteed that the graph is going to be small enough to fit into maybe a cache line, in which case, maybe the matrix implementation was good enough anyway, you're going to find that this is going to be slow. And so you do often have to choose which of these implementations you want. The NetworkX implementation is actually fairly similar to the CS graph or the sparse graph from SciPy. And the alternative is really the dense implementation written in NumPy. And so you can see there's a little bit here that makes it a little bit difficult. Now, I do have a challenge that I'd like to share with you. Because when we talk about these modelings, it gets a little bit tricky for us to do something with these modelings. And so I want to leave a challenge in your mind. Given a very large graph, where we really will have to make a choice between do we use the adjacency list modeling or the matrix modeling, where that graph is nearly bipartite, which we'll talk about, color bands of nodes such they're either red or blue, and do a shortest path following a policy. This is one of the downsides of NetworkX. If you happen to have some slight rule on whether you can follow a node or not just minimize over the weight, but only be able to follow a node if you're going from one coloring to another coloring, then it's almost impossible for you to make use of NetworkX here, and you have to rewrite these things from scratch. And even if you rewrite these things from scratch, they're going to be operating at the pure Python level, and it's going to be very slow.